Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder a component in Vero board. Use a soldering iron as sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated Vero board for your prototyping. In our previous session, we have learned that how to generate the PWM signal and how to convert the PWM signal into analog voltages. We have written a program to generate the PWM signal for 1 kHz frequency, and we have controlled the duty cycle of the PWM signal from 0 to 100% with a resolution of 8-bit. In this session, we will learn that how to display the feedback voltages on LCD display. And now we'll insert the LCD display in our prototype, and we'll write a program to display the feedback voltages on LCD display. And we have studied in our previous session that PIC16F877A microcontroller has 8 analog input channels, and we have also learned that how to configure the bits of ADCON1 register to configure the analog input channels. If we'll assign the value that is 02 to ADCON1 register, then the 3 channels, that is analog input 5, analog input 6 and analog input 7, will be configured as digital input output, and the 5 channels, that is from analog 0 to analog 4, will be configured as analog inputs. And here we can find a prototype to read the analog input channel, that is variable as integer, ADC read channel number. We have already interfaced 2 variable registers with analog input 0 and analog input 1. Now in this session we'll interface the feedback value of PWM to analog converter on analog channel 2. And here we can find the feedback 1, which is connected on pin number 4 of the microcontroller, which is analog input 2 for this microcontroller. Now we'll write a program to read the feedback voltages on analog input 2, and we'll display the voltages on LCD display. In our previous session, we have developed a circuit to convert the PWM signal into analog voltages, that is from 0 to 10 volts. And we have used a variable resistor to attenuate these voltages to 5 volts. And we have used a unity gain buffer to interface these voltages to the microcontroller. And we have connected this buffer signal to the analog input 2 of the microcontroller. And we have used an operation amplifier, that is LM358, as buffer. And we have also studied that ADC of PIC16F877A microcontroller will convert 0 to 5 volts into equivalent digital number, that is from 0 to 1023. 0 to 5 volts will be converted into an equivalent number, that is from 0 to 1023. It means that the digital number 0 will correspond to the 0 volts, and the number 1023 will correspond to 10 volts. And if you would like to display, that is 1023 as 10.0 volts, then we'll divide the number, that is 1023, by 10.23, which will give us the number that is 100, and we'll display the number 100 on LCD display as 10.0 using a decimal point. Now we'll write our program to display the feedback voltages on LCD display using microC compiler. And here we can find our previously written program to generate the PWM frequency of 1 kHz. And we have written a program to increase or decrease the PWM duty ratio with the help of 2 switches, that is increment switch and decrement switch. Now we'll modify this program to display the feedback voltages on LCD display. First we'll understand this program, then we'll modify this program as per our requirement. Here we can find we have defined 2 switches, that is increment switch and decrement switch. Increment switch is connected on port RD4 and decrement switch is connected on port RD5. We have also defined 3 variables, that is unsigned short, duty register, unsigned integer, increment delay register, unsigned integer, decrement delay register. And here in main program before while loop we have configured port RC2 as output port. We have called two prototypes before while loop, that is PWM initialize for 1 kHz frequency and PWM start. And we have used third prototype, that is PWM1 set duty in while loop. And here we can find we are calling a subroutine, that is switch read routine. And in switch read routine we have written a program to check the status of two switches, that is increment switch and decrement switch. If the increment switch will be pressed, then our program will come into this if condition, and it will check if the value of increment daily register will be greater than or equals to 2000. Then our program will come into this if condition, and in this if condition it will check that if the value of duty register will be less than 255, then our program will come into this if condition and it will increment the duty register. After incrementing the duty register by 1, our program will reinitialize the increment daily register to the 0 value. After executing this routine, our program will come into the second part of our program, and in this routine our program will check if decrement switch will be pressed, then our program will come into this if condition. And in this if condition our program will check if the value of decrement daily register will be greater than or equals to 2000, then our program will come into this if condition, and here it will check if the value of duty register will be greater than 0, then it will decrement the value of duty register by 1, and after decrementing the duty register by 1 it will reinitialize the value of decrement daily register to 0. Before leaving switch read routine, our program will increment both the register, that is increment daily register and decrement daily register. And now we'll modify this program to read the feedback voltages of PWM to analog converter circuit. Before writing our subroutines to display the voltages on LCD display, first we'll go to the help, and in help we'll go to the Micro C Pro for PIC libraries, and here we'll go to the LCD library, and here we can find in sample program that LCD display is initialized for port B, and here from schematic we can find that we have also interfaced the LCD on port B. To initialize the LCD display on port B, we'll copy these assignments from sample program, Ctrl C, and we'll paste these assignments here in our program, Ctrl V. Now here in Micro E libraries, in system libraries, we'll select LCD library, and we'll go to the help again, and here we can find different modules, that is LCD initialize, LCD command LCD clear, LCD command LCD cursor off, and how to print the text on LCD display, that is LCD out on row 1, column 6 and text 3. So first we'll copy these three modules from the sample program, that is Ctrl C, and we'll paste these modules in our main program. So we'll paste these modules here in our main program, Ctrl V, and now we'll go to the help again, and here we can find that how to define a text array to print the text array on LCD display. Now we'll copy this assignment from here, Ctrl C, and here in assignment section we'll write text assignments. So we'll write, now we'll paste the text assignment here, Ctrl V, and we'll modify this text string as per requirement of our program. So here we'll write digital voltmeter. The length of the string is 18 character, and you know that we are using a LCD of 20x4, so we'll add two spaces in this string to print this string in the middle of the LCD. We'll add one space before this text and one space after this text. Now we have adjusted the length of the string for 20 characters. Now we'll copy this assignment from here, Ctrl C, and we'll paste this assignment once again, Ctrl V, and we'll change the text, that is 2, and we'll change this text string to print the text on second row of the LCD display. So here we will write volts equals to VV.V. The length of this message is 12 characters, so we'll adjust the length of this message to print this message in the middle of the second row. So we'll add 4 places before this text, and we'll add 4 places after this text. We'll print decimal place, unit place and 10 place of the converted voltages at the place of V. From this text message we can find that where to print the decimal place digit, where to print unit place digit, and where to print 10th place digit. So from this text we can find that we'll print the decimal place on 16th position, unit place digit on 14th position, and the 10th place digit of the converted voltages on 13th position. And now we'll go to the help again, and from the sample program we can check that how to print the text on LCD display. So I'll copy these two commands from here with the delay prototype, Control C, and we'll paste these commands here in our main program, that is Control V. Now here we'll assign the value to the ADCON1 register, that is 02. So we'll write ADCON1 equals to 02, and now we'll call a subroutine to read ADC channel. So here we will write ADC read R, that is ADC read routine. So here we'll add a comment and we'll call the ADC read routine before main program. So here we will write, that is void ADC read R, and we'll write the ADC read routine between these two braces. Now we'll go to the help, and in help we'll go to the ADC library, and here we can find the ADC library routines. So first we'll initialize the ADC using this prototype, that is ADC initialize. So we'll copy this prototype from here, that is Control C, and we'll paste the prototype for ADC initialization here in our main program, that is Control V, and we'll go to the micro E libraries, and here in system libraries we'll select the ADC library, and from the sample program we can check that how to read the ADC channel. So we'll copy this prototype from here, Control C, and we'll paste this prototype here in ADC read routine, Control V, and we know that we have connected the feedback voltages on ADC channel 2. So here we can find a number, that is 02, so there is no need to change this number, but we have to assign a variable to read ADC channel 2. So we'll declare a variable in our variable assignments. So here we'll define another variable, that is unsigned integer, that is ADC reg equals to 0, and we'll copy this variable from here, Control C, and we'll replace this variable from the new variable, that is Control V. Now the analog voltages from ADC channel 2 will be stored in ADC register. Now we'll define another variable to convert this ADC raw data into the voltages. So here in variable assignments we'll define another variable, that is unsigned integer voltage reg equals to 0, and we'll copy this variable from here, Control C. So we'll paste the variable here in ADC read routine, Control V, equals to ADC register, Control C and Control V, and we'll divide this raw data by 10.23. In this case the maximum raw data, that is 1023, will be converted to the number, that is 100. Now we'll print the converted scale data on LCD display. So here we'll call another subroutine, that is LCD print routine. So we'll write LCD print R, and we'll add a comment, LCD print routine, and we'll call the LCD print routine before main program. So here we'll write, that is void and we'll write the LCD print routine between these two braces. In hardware libraries we'll go to the LCD library, and here we can find a prototype, that is LCD character, row as character, column as character, and the character to print on LCD display. We'll use this prototype in our LCD print routine. So here we'll write LCD character, LCD row, that is 2, and the column, that is 13. So we'll copy this variable from here, Control C, and we'll paste this variable here in this prototype, that is Control V, and we'll divide this variable by 100, and we'll also adjust the decimal place, that is %10. To print this character on LCD display, we have to convert this number into equivalent ASCII number, and from the tools we can go to the ASCII chart, and here we can find the equivalent ASCII number for 0 is 48, So here we'll add a constant, that is 48, to convert this number into equivalent ASCII. Plus 48 Now we'll copy this command from here, Control C, and we'll paste it here, Control V, and we'll change the column position, that is 14, and we'll divide this number by 10. Now we'll print a decimal point on 15th column of LCD display, so we'll write LCD out row 2 column 15, and the text will be decimal point. Now we'll print decimal point digit on 16th column of LCD display, so I'll copy this command from here, Control C, and we'll paste it here, Control V, and we'll modify the column to print the number on LCD display, that is 16, and there's no need to divide this number, we have to adjust the decimal place only. So here we have completed our program to display the voltages on LCD display. Now we'll compile our program and we'll check the result of our program on our prototype. Here we can find a syntax error on line number 76 of our program. So here we have to place another round bracket, that is like this. And now we'll compile our program once again. Okay, now there is no error in our program. Here we can find we have selected the power supply jumper for LCD display. Now we'll power up the prototype and we'll observe the result of our program. Here we can find the second row is misprinted on our LCD display. Let's find the reason of this problem in our program. And here we can check we are printing the second text on second row and fifth column. So we'll change the column to 1. And now we'll incorporate a delay in our ADC read routine and LCD print routine. So we'll define two more variables. And here we'll define two more variables to produce delay in our ADC read routine and LCD print routine. So here we'll write unsigned integer ADC delay reg equals to 0, and we'll define unsigned integer, that is LCD delay register equals to 0. Now we'll use these two variables in our ADC read routine and LCD print routine. So here we'll use ADC delay register, so we'll write, that is if ADC delay register will be greater than or equals to 1000, then our program will come into this if condition. And here we will reinitialize the value of ADC delay register, so we'll write ADC delay register equals to 0, and if the value of ADC delay register will not be greater than 1000, then our program will increment in ADC delay register. So here we will write ADC delay register. So here we have incremented in our ADC delay register. Now we'll use a second variable in our LCD print routine. So here we will write, that is if LCD delay register, if it is greater than or equals to 1000, then our program will come into this if condition. And after displaying the characters on LCD display, we will reinitialize the LCD delay register. So here we will write LCD delay register equals to 0, and if the value of LCD delay register will not be greater than 1000, then our program will increment in LCD delay register. So here we will write, that is LCD delay register. So here we have incremented in our LCD delay register, And here on second row, we'll also display a letter that is V after displaying the voltages. So here we will write that is V, and we'll adjust the length of the string. And now we'll compile a program and we'll test the result of our program on our prototype. Here we can check the output voltages for PWM to analog converter circuits are 0 volts, but we are getting 1.1 volts at feedback voltages. The reason for these offset voltages are the open circuit for PT100 amplifier, because we have connected no PT100 sensor in the feedback circuit of PT100 amplifier circuit. So we'll place a 100 ohm resistor instead of PT100 sensor, because the resistance of PT100 sensor is 100 ohm at 0 degree centigrade. And here we can check we are getting 5.9 volts at the output of PT100 amplifier circuit. Now we'll replace the PT100 sensor from 100 ohm resistor because we are not using a PT100 sensor in this project. Here we have replaced the PT100 sensor with a 100 ohm resistor. Now we can check we are getting 0 volts on LCD display, and we can check at the output of PT100 amplifier circuit. Here we can check we are getting 0.02 volts at the output of PT100 amplifier circuit. Now we'll check the output of our PWM to analog converter circuit, and now we'll increase the duty cycle of the PWM signal. And here we can check we are getting 1.09 volts at the output of PWM to analog converter circuit, and here on LCD display we are getting 1 volt. Now we'll increase the duty cycle of the PWM signal further. And here we can check we are getting 5.07 volt at the output of PWM to analog converter circuit, and our digital voltmeter displaying the 5 volts on LCD display. Here we can check the maximum output voltages of PWM to analog converter circuit, and we are displaying 10 volts on our digital voltmeter. Now we'll decrease the duty cycle of the PWM signal. So in this session we have learned that how to display the feedback voltages on LCD display. We have generated a PWM signal of 1 kHz from the microcontroller, and we have converted the PWM signal into analog voltages, and we have displayed the feedback of the analog voltages on LCD display.